Welcome back, my fellow colleagues. This is 26, remove duplicates from sorted array. Okay, this one, not too bad, but it's probably a little bit difficult actually if you don't have a mental model, but it's not too bad. There's a few different ways to do it that's a little bit cheeky, but the one I'm going to be showing you today is like the most reusable. It's the most templatable. You'll be able to find. You'll be able to use this pattern in a lot of different problems in different ways. So what's the problem, right? So given a sorted array nums, remove the duplicates in place, keyword here, such that each element appears only once and returns the new length. Do not allocate extra space for another array. You must do this by modifying the input array. They say it again, in place with constant memory, right? So you're thinking, oh, this is just an array problem, but it's a duplicates problem, but they want you to remove the duplicates, right? And that's pretty simple, right? When you can use linear space, right? You could do a few different things. You could, they said the array was sorted, right? So you could loop through, let's just say a dictionary. Loop through the list, create a dictionary of numbers to occurrences. Since the numbers are guaranteed to be sorted, which this problem says, what you can do is just save numbers in the dictionary, and then once you can just loop through the dictionary again and just shoot out the numbers, right? And so basically you'd end up shooting out the numbers in the correct order with only one occurrence, right? But a few problems with that. They want this array to be modified in place, right? And so we can't do that, right? And we're supposed to do this with a constant memory, right? And if we did that, we'd be using linear space, so that's not good. I feel like there's one more thing. And so that's what we have so far, right? And so if we look at some input, we'll see is we have an array 1, 1, 2, right? Obviously the duplicate here being 1. And so they want us to output the length of the completed array, right? And so we're going to modify the array in place, which they're going to check because this is going to be passed by reference. They're able to check whether or not the array is correct, and we also have to pass the correct length of the array with removed duplicates, right? So if you take a look here, the starting array length is 3. 1 is the duplicate here. We remove the duplicate. Now we have an array of just 2 elements, and so our output is the 2, which is the length of the array after we remove the duplicates. Same thing with this one. They remove a bunch of duplicates. The output here is just the numbers in order. And this one is a good example of what I meant earlier, how you could do this with a dictionary. If you were to make this a dictionary, you could just save every number that you run across, and since it's sorted and there's supposed to be no duplicates, you can just poop out the numbers in the same exact order you saw them, and you get the answer that way too. But that's linear space. We can't do that. If we look at the constraints here, we'll see, which is always important to look at, you always want to handle your edge cases, that nums is always sorted in ascending order. Not particularly important. We just know that it's sorted. This algorithm is going to work either way. What's important to note is that the length is going to be equal to 0 or 3 times 10 to the 4th, right? So we have to handle arrays of all those lengths, right? And so the first thing we're going to do is we're going to I'm going to walk you through the problem with the scaffolding, and then we'll draw it out afterwards, and so it's going to make a lot more sense. So how do you get started with this problem, right? So you might be thinking, oh, I should get started on the algorithmic portion, right? But oftentimes in these problems, you can get started just by cranking out a few base cases, right? So we know that our array length can be from 0 to 3 times 10 to the 4th. But there are 2 elements in there, or 2 lengths in there, where we already know the answer, right? So there's no point in wasting any time. So those 2 lengths would be a length of 0, right? Because there's nothing in the array, just means there's no duplicates to remove, which means that the length post modification, though there's nothing to modify, is going to be the same as the length of the array that was passed in. Same thing with 1. So there'd be 1 number in the array, right? There's only 1 number in the array, so there's no duplicates to remove. So the answer that they want us to return, the modified version, would literally just be the length of that array. And so I guess what I'm saying here is that for arrays of length 0 or 1, there's nothing for us to modify, therefore remove, and so the answer, it will be the length of the array that's passed in. So we can get started on that by saying if len of nums is less than or equal to 1, we're just going to return length of nums. So it's just going to catch both of those cases, right? If we're 0, If there's no elements in the array, then return that we modified nothing, and the length is the same as we passed in. But now we have to get to work, right? And so the pattern we're going to be using here is the 2-pointer pattern, right? And so the idea here is that you have 2 pointers, right? And let's just make a bogus list here. The bogus list being that you have 2 pointers, right? And there's a few different ways to do this. Sometimes the pointers can move at different speeds. So I'm going to use a star for the first pointer and a caret for the other pointer. And basically what you have is these 2 pointers. Sometimes you have one that moves a lot faster than the other one. Sometimes you have one starting at the front and one starting at the end, and they both iterate towards each other. In the case of if you have to reverse a string in place, you can have them both increment towards each other and just swap the values at these indices, right? And so for this version, what we'll do is just have, we'll do the slow and fast version of this. And slow and fast just means, or rabbit hare just means that one of them is faster than the other one, right? Or one of them is always ahead of the other one. So our caret here is going to be rabbit, and then our tortoise here is going to be the star. And basically, the rabbit's always going to be in front of the tortoise because the tortoise is slow, right? And so what happens is we start like this, right? And we say, hey, are these 2 numbers, right, are they the same? If they are the same, well, then we have a duplicate, right? So we should remove one of these, right? And so that's pretty good, right? But our list would kind of stop here because we're kind of done, right? And so you'll see that the end case is when the tortoise is too far, right? And so if we were to take a slightly bigger list, actually, we're just going to start on the algorithm and then I'll draw the rest afterwards. But to get that going, we're going to have a few different things. So because we have to remove the array in place, right? We have to remove the element from the array in place, right? We need a while loop. So why do we need a while loop, right? You can do this in place another way, but this is the easiest way that transports to different languages pretty easily. So if we do while, and we're just going to make a pointer 1 is going to be equal to the first index, remember? And pointer 2 is going to be equal to the second index, right? And we can say this safely because we've screened out arrays that aren't big enough, right? So this is another point of why we screened out these 2 arrays, right? Because we need 2 pointers at minimum in the list to get our solution. So we've screened out all possible scenarios where that's not true. And then we're going to say while pointer sub 1 is less than end, and then we're going to make end here, and so end is just going to be the last point in our array, right? And so the last index in an array is always capacity -1, so we're doing lengths of nums -1. And then what we're going to do is we said, remember, if nums sub pointer sub 1 is equal to nums sub pointer sub 2, which means those 2 numbers that we saw, they're right next to each other, means they're the same, they're a duplicate, we're going to have to remove one of those numbers, right? It doesn't really matter which one you move, but it's important to note that the function we're going to use for this is nums.pop, and we're going to pop it at pointer 1's place, right? And why is this important to know is because when you're removing an element in an array, right, anywhere that's not the end, basically, if you remove this element, right, you have an open slot in the middle. So all elements have to be slid down to that open spot to close up that open space, right? And so theoretically speaking, if you have a much larger array, the worst case is that you move if you have, like, you know, it's always easy to remove from the end, right? Because you can just pop it off, right? It's always instant. But anywhere else, if you remove it from the front, then you have to linearly slide every single element from the back to the front to close up the space that we opened up. So just know that this operation, worst case, is linear time. And since we removed an element from the array, and I'll display that here, let's just say we're doing this, right? If we removed an element from the array, right, our end is equal to 3, right? So 0, 0, 1, 2, 3, right? But we removed an element from the array. It was a duplicate. So now our array is inevitably doomed to go out of bounds, right? And so what's the obvious choice here, right? The obvious choice, right, is to decrement end, right, when we remove an element from the array. So this will always keep us in bounds. And this is why we used for loop. I mean, in for loop you can still modify the number that you initialize, but I think the logic is a little more easier to follow with a while loop because it's more explicit. And so that being the case, right, that means we handled the case where the numbers are duplicates, right? So if they're not duplicates, then what do we want to do, right? So let's just say in a case like this, we have 1 and 2, they're not duplicates. Well, that's good, right? We'll have the hare move up once and the tortoise move up once again. Well, are these two numbers duplicates? And so the logic that I'm hinting at here is that pointer 1 plus equal 1 and pointer 2 plus equal 1, right? And then there you have the logic for the oops, I got to take out this extra stuff. And there you have the logic for handling 2 pointers. So in a lot of different algorithms, you can do these differently. You can have one of them, you can have the second one move over like 5, right? Or, you know, if the algorithm necessitated or the problem necessitated that, then you could kind of mess around with how it's done. And so the time complexity here is actually going to be linear time, right? Because we're kind of linearly iterating towards the end of the array, right? Even though we pop an element off the back, it's we're decrementing end. It's because we removed an element from the array. And what's the space complexity? Well, this is constant space, right? That's what they wanted from us, right? We're not saving all the things we pop into a different answer. We're not using a dictionary. We're just using a few variables that are going to be the same no matter the length of the list passed into the function. So basically the memory that we allocate to solve this function is going to be constant, or I guess it's not tied to the input to the function. And so now we're going to draw this. A very short example we're going to do. Boom. So what's going on, right? So I have the same, what we just did, except I have it over here instead. Let me make some more space. And so we have this dummy array here, has 1, 2, 2, 3, 2, the double 2's obviously being the duplicates that we want to remove. We have pointer 1, which has been set to 0, just like in our solution, and pointer 2, which has been set to index 1, just like in our original solution. And end is equal to 3. Remember, because we said that end was always the last element in an array was always the capacity minus 1. There's 4 elements. Minus 1 gives us 3, right? So from here we can kind of work through the code we wrote. Okay, and so I've added the code that we're actually working with here so that we can see how it's happening in real time. And so let's just start, right? We said pointer is equal to 0, it is. Pointer 2 is equal to 1, it is. End is equal to lens of nums minus 1, it's 3. Makes sense. So while pointer 1 is less than end, well, 0 is less than 3, that works for me. Let's run through the checks. If nums pointer 1 is equal to nums pointer 2, well, pointer 1 is at the 0th index, pointer 2 is at the 1th index, right? Are these numbers the same? They're not, right? And so what do we say we would do in that case? We'd say pointer plus 1 to both of them, right? And just move them forward. Nothing interesting is happening here. So we'll cross this out, make this 1, cross this out, and we'll make this 2. Right, and now we'll start over. It's a little bit painful to do over and over again, but it's important to do it over so that you can see like what's actually happening. And so we'll start over. We'll say if is pointer 1 is less than end, well, 1 is still less than 3, so we're still good to go. If nums pointer 1 is equal to nums pointer 2, is that true? Well, the 1th index is 2, and the second index, which is actually the third index, so 0, 1, 2. So these two numbers are the same. So we've hit a match here, right? So what do? We said, okay, well, nums.pop pointer 1. Nums.pop is an array function in Python that just removes an element at an index. It's going to say, hey, remove whatever's at pointer 1, because that number is making this list a duplicate, right? So we'll say, we'll bonk this, right? And then we'll draw the list again without the duplicated elements, right? And this is what our list looks like now, right? And then we said, hey, after you remove the element from the list, do end minus equal 1, right? Because our end was the third index, 0. If we look at this in index, 0, 1, 2, there's no longer a third index, right? So we're going to say, hey, change end to 2. And then we're going to go to the next iteration, right? And so now let's keep going. We said while pointer 1 is less than end. Well, pointer 1 is 1 still, so we're still less than 2, which is end here. And so let's check again. If nums pointer 1 is equal to nums pointer 2, well, these 2 points, so P1 is at index 1 and P2 is at index 2, they're not the same, right? What did we say we would do if that happened? Well, we'll just increment both pointers, right? And so pointer 2 is going to go out of bounds, and we're going to increment both of these, right? And so this array looks pretty good, but we're just going to keep going. So we finished another iteration. So while pointer 1 is less than end, and then we're going to say, wait, pointer 1 and end are equal to each other, which makes this case pointer 1 less than end not true. So that means we're done moving through the array, and then we're going to return the length of the new array, which is just length of nums, which is 3. And so that's why this works pretty well. And some of you might have noticed that when we remove an element from the array, right? When we remove an element from the array, we don't increment anything, right? And that's important, right? Why do we do that? So let's take the case where we have something like this. Right? And let's just humor me that P1 is at 1 and P2 is at this other one, right? Now, our thing said if they match, remove them, right? So we'll remove this one. We'll draw an X over it. We'll redraw the array. Boom, 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 boom. Now, P2 was at the 1th index, so 0, 1. So P2 is still here. And, I mean, P1 was at the 1th index, it's still there. And P2 was at the 3rd index, so 0, 1, 2. So P3 is actually still here, right? And then once we get on that next iteration, what we'll see is that why we don't increment pointer 1 and pointer 2 and they're the same is that there could be multiple duplicates, right? And so this is what happens again. We remove yet another duplicate, and you get the same, you get the correct answer. And you only want to move forward when we know for a fact that there's no more numbers that are being pushed into here that are different, that are the same. And so that is 26 remove duplicates from sorted array.